Welcome to tutorial number 11. I'm going to talk about the vapor parameter XCrush in this video. XCrush modulates the content of the grains, but there is no external modulation source. The content of a grain is modulated by the content of the following grain as long as these two grains overlap. No overlapping means no XCrush effect. And only grains of the same grain stream, the same generator, do modulate each other. There is no modulation going on between overlapping grains of different generators of different streams. The manual doesn't tell us exactly the mechanism how XCrush works. The manual calls it an asymmetric ring modulator algorithm. Well, let's do some research of our own to find out what we need to know about XCrush to compose and produce our pieces. There are obviously the following parameters which influence the result of XCrush: the length of the grains, their rate of birth, and the relationship of both parameters, the sonic content of the grains, of course, and the type of the grain window. The grains fade in and out, and so does XCrush in the overlapping area. And perhaps the speed of playing back the grains. And finally, we have to find out how XCrush reacts when we modulate all these parameters. Let's start with length and birth. I adjust XCrush at 100% and I choose a sine wave as the grain's content. It should show the goings-on more clearly than other more complex waveforms. I'll apply some reverb to emphasize the changes of the sound. The sequence you hear as a kind of test tone is just a series of Cs with different lengths. And all of you who would like to revive their knowledge about the goings-on at very short lengths of the grains may watch tutorial number 9 again. At first I choose a length to birth relation of about 2 to 1, precisely 100 to 49. So 50% of the grains overlap. With grain lengths between 1 millisecond and about 8 milliseconds, we get bell-like sounds. From 9 milliseconds to 18 milliseconds, the sounds get more and more machine-like. And from 19 to 38 milliseconds length of the grains, there are some nice drones. Above 38 milliseconds, more and more higher frequencies occur. But at about 60 milliseconds, the changes in the modulations start getting less and less. And at about 90 milliseconds, there are almost no changes of the modulations at all. Above 90 milliseconds, the perceived pitch decreases, but higher frequencies occur. At about 300 milliseconds, the modulation begins to fluctuate. Summary: the strength of the modulation fluctuates while a tone is played. With short grain lengths, the fluctuation isn't clearly to be noticed, but the longer the grain's duration get, the lower is the frequency of those fluctuations and the less influential for the overall impression of the sound does XCrush get. I decrease the region of overlapping and choose a length to birth rate of 100 to 74. Only 26% of the grains overlap now. With grain lengths of 1 to 3 milliseconds, the sound has the character of silence. Between 4 and 45 milliseconds we get drones and machine-like sounds and the perceived pitch decreases. Between 45 and 100 milliseconds the sound doesn't change much. From 100 to 250 milliseconds we see and hear typical amplitude modulation effects and a decreasing of complexity of the modulations. Between 250 and 800 milliseconds the sound stays more or less unchanged. Increasing the length of the grains above 800 milliseconds, the low frequency fluctuation of the modulation set in again, and the longer the duration of the grains is, the more dominant gets the unmodulated sine wave. Summary: again, the longer the grains, the less influential is the modulation. But there is a difference to our first experiment. The regions of strong modulations are smaller, with only 25 or 26% overlapping grains. Let's go on to a length to birth relation of 100 to 90. Only 10% of the grains overlap. We get bell-like sounds with grain lengths of 1 up to about 4 milliseconds. With a duration of about 5 and 6 milliseconds, the perceived pitch decreases. But at 7 milliseconds up to 40 milliseconds, the perceived pitch increases again. With grain lengths of more than 40 milliseconds, the modulation gets weaker, less influential, and at about 150 milliseconds there is only a fluctuation of the sine wave's loudness without changing the sound, the timbre. Summary: in accordance with the last experiment, the region of influential XCrush modulation is even smaller. Let's go to the other direction now. I increase the percentage of overlapping by choosing a length to birth relation of 100 to 25, meaning 75% of the grain's length overlap. Between lengths of 1 to 12 milliseconds we get bell-like sounds again. Between 13 and 40 milliseconds, the sound gets machine-like. We get drones and the perceived pitch decreases. There are no changes perceivable in the sound between 41 and 60 milliseconds. From 60 milliseconds up to 85 milliseconds, the perceived pitch returns to the original frequency of the sine wave. From 85 milliseconds up to above 1000 milliseconds, the modulations get weaker and less influential and are reduced to more or less common classical amplitude modulation. And above 1000 milliseconds up to 60,000 milliseconds, the strength of modulation as well as the loudness fluctuate with even lower frequencies. Summary. The basic behavior of XCrush stays the same, but the regions of modulation are wider, larger again, without reaching the extent they had with 50% overlapping. And at least 90% of the grains overlap with a length-to-birth relation of 100 to 10. There is only one kind of modulation, whatever grain length we choose. It is a rhythmical knocking of two sidebands. The sine wave dominates the sound all the time. Summary. In complete accordance to all of the experiments, there isn't nearly a region of grain length with explicit modulations. Overall summary. The most influential and most manifold modulations we get with a 2-to-1 relation of length and birth, with 50% of the duration of the grains overlapping. We have to tell apart changes of the sound because of different raw material, different sounds we feed into CrusherX, from changes because of a perhaps even fundamentally changed way XCrush modulates those inputs. Of course, does a sine wave sound different from a saw, modulated or not modulated? The question is, does XCrush handle a sine wave differently from a saw? With a saw wave, it's more or less the same, but for the fact that, of course, the timbre is richer. The summaries we came to using a sine wave are valid even with saw waves. The two following situations may be sufficient to demonstrate how a saw wave interacts with CrusherX and the XCrush parameter. First, at a length-to-birth relation of 100 to 49, like in the very first of our last experiments, the only basic and general difference is this: the bell-like sounds end already at 3 milliseconds. Second, let me just demonstrate an impressive drone sound. The relation length to birth equals 100 to 25, like in the fourth of our experiments with a sine wave.